Hello, today it's my pleasure to talk about finite differences. So, finite difference today, this is based on Taylor's series and Taylor's theorem. We're going to talk about forward, we're going to talk about backward, we're going to talk about centered, and we're going to talk about what order means in all of this. Remember our Taylor's theorem. This was an amazing theorem that made something perfectly equal. It was that you would have this function that is n plus 1 times differentiable, and you would say, I want that function evaluated at the zeroth derivative and all of the derivatives up to, but not including n plus 1, and I'm going to evaluate all of those derivatives at the home position or the reference x sub I, and I'm looking at a step. The step is going to be h. That's going to be from x sub I to some x sub I plus 1. That's the next position. Okay, so I look at all of that and I go up to the nth derivative on this thing, and if I do that, it's gonna, and I include this remainder term or this error term that's evaluated at the n plus 1 derivative for some c value, divided by n plus 1 factorial times h plus n plus 1. This is a perfect equality. First time I saw this, I said, there's no way. But then, I started warming up to it. We call this notation R sub n. We call it an order, call it the big O notation. That's what the math nerds call it. And they say, okay, it's of the order h to the n plus 1. So if the h is very, very small, like it should be, each time that you square it, you're getting something that's much, much smaller. So h is smaller than 1. So every time, much smaller than 1. And every time you square it or take it to a new power, that gets even smaller and smaller. And then when your h is to an n plus 1 power, that should be minute. And then you're dividing each term, you're dividing by something factorial. And as you get to n plus 1, you should be dividing by a big number. So unless this nth plus 1 derivative is very, very sensitive, that's the only way that this remainder term can get big. But generally, this remainder term is small, and that's why being of a higher order kind of helps us, okay? In this c, it's weird that this c is somewhere between our reference point and our next point, but we don't know exactly where, and it turns out it doesn't matter. Again, if this is small, it doesn't matter. But the Greeks call this, that's the letter X in Greek, and I call it kasi. That's as close as I can get to pronouncing it. Okay, so definition of a derivative, I think everyone knows this. It's going to be the limit of the next function value evaluated at the next point minus the current point divided by the step as the step goes to 0. We can approximate that. If h is small, we can approximate it like this. And if we want to quantify that error of the first derivative, we think about Taylor's theorem. We could write it out in this way, where the c value is somewhere between x and x plus h. And we're thinking about this, we're thinking about taking it to the n plus 1, in this case being 2. So this is the first derivative approximation. So if I take this equation and I rearrange it, so I do this quite often, I rearrange it in this way so that I can show that remainder term, after I divide through by h, that remainder term is to the h power. So that's a first order. So when I get that remainder term on the right and having it divided by h in this case, now what remains is to the h power. So this is a first order approximation for my first derivative. Okay, so let's see if we can use that in our forward difference. So our forward difference, we can think of, we're at the current reference point, and we're going to step forward our h to our x at I plus 1, and we're going to look at that slope there, or that approximation of the true slope, the true derivative. So that's what we're going to think about here. And we're going to be writing it in this way. And we can think about h as being x plus 1 minus x at I plus 1 minus x sub I, and x as being x sub I, so we substitute that in. So that's our first order forward difference derivative right here. So that's what it looks like. First order forward difference derivative. Forward because you can also think about it in this way like we had earlier. So we're stepping forward. Again, where my c is somewhere between my current value and then the next one. Okay, so here I want to prepare you for the backwards difference, okay? So forwards difference, here we were stepping with plus h, but we want to think about h as always being a positive value stepping forward. So what I want you to do is I want you to keep your h in your mind as being a forward or a positive value. So if we do that, then we can think of stepping backwards by making it a minus h. So wherever we would have an odd-powered derivative, when we start expanding, odd-powered derivatives would get a negative in front of it if we're stepping backwards. So this, I think, upsets some students, but you have to be consistent in what this h is, because we're going to be stepping forwards, we're going to step backwards, we're going to step forwards multiple steps, we're going to step backwards multiple steps. So we need to make sure that we keep our h consistent. So keep your h in your mind as always being positive. If we do happen to step backwards, stick a minus sign there in front of the odd-powered terms. The even powers are going to go back to a plus because you're going to have minus h quantity squared. So it goes back to a plus. So it's alternating derivatives will get the negative sign. Okay, so let's write our first derivative in this way. So it's going to be x sub I minus f of x sub I minus 1. So if we take this equation and rewrite it to solve for f prime, you're going to see that would be f of x sub I minus f of x sub I minus 1 divided by h. And it works out that the x minus x sub I, so x minus x sub I evaluated the function divided by h being a positive. So now that's the slope that that's the approximation of the true slope. So that's what it looks like, and pretty good. All right, so now we're going to take what we had as a backwards difference, first order derivative, and we're going to talk about a centered difference. Okay, so what we're going to do is we're going to take the previous two. We have our forward and we have our backwards. Okay, and note that in each of these I've added a c term. I've taken the c term and moved it one to the right, one order or one derivative to the right. So earlier my c was a second derivative. Now my c is in third derivative. Okay, and so I've got my x sub I coming back in for my second derivative, and I've got my third derivatives with the c's, and I've got my backward steps getting a negative sign for the odd powered h's and the odd powered or odd derivatives, and then my even derivative is a plus. So everything is consistent. I'm just growing it to the right with my c's, and my c for the for my c1 for the first one is going to be between my reference position and the next one, and my c2 is going to be between the reference position and the previous one, because that's a backward step. All right, so you guys should be very comfortable now with how I've explained these two equations. You need to be, if you're not comfortable with how I've explained these two, you need to go back into the previous few moments. Okay, so I'm proceeding now thinking that you're comfortable with how I obtained those two equations. So what I'm going to do is I'm going to subtract the two equations. I'm going to take this minus this, which gives me that. I'm going to take each term, that term minus this term minus that, this term minus that, this term minus that, this term minus that. And what happens is the function kills itself, right? So this minus this is 0. This minus this gives me 2 of the first derivatives times h, all right? This minus this kills itself, so the evens are getting killed, and the odds are combining when I subtract. So I'm going to have the third derivatives are going to combine, and I've kept them separate like this, and I don't have to because we're going to end up not worrying about them in a minute. But I just wanted to kind of keep them hanging around here so that you could see that I get to a point where I'm going to get the f prime over on the left-hand side. I'm going to divide by 2h. So once I divide this by 2h, I'm going to get 12. And this h cubed goes to h squared. Okay? So what happens is this error term, so I've got another expression for for the first derivative. I've got another expression which is on the order of h squared. So that's a better approximation of first derivative, and I'm using a forward point and a previous point and dividing by 2h to get that first derivative, but it's going to be better because it's second order. And that's what they say. So this, you can kind of see it here. So I'm taking x of I plus 1 and x of I minus 1, and I'm dividing by 2h. So that gives me a better approximation, this approximation to the true slope. Okay, so the book says use centered when you can because it's going to be more accurate. The first point, if you have a series of points, the first point you have to use forward, and the last point you have to use backward. But the points in the middle you could use centered. This is what the book says. But for me, if I'm doing real-time control, I don't have the future points yet. So I'm always kind of using the backward difference to figure out what the whatever derivative is that I want to use. Okay, so that's what I look at. Okay, let's look at getting some other derivatives. So I could go back to those same two. And here's what I'm going to do is I'm going to push my Cassini even one more to the right. So now I'm talking fourth derivative for Cassini 1 and Cassini 2. I've got my h to the fourth. I'm bringing in third derivative of x sub I. I've got the odd derivatives are getting the negatives. The even derivatives are getting the positives on my backward step. So everything is like I've said. You should understand what I'm talking about here. If you don't, go back a few slides. If you do, let's forge on. So again, my Cassini 1 is going to be, it's a forward step, so it's going to be between my current point and the next point. And my Cassini 2 is going to be between the previous point and the current point because the Cassini 2 is a backward step. So now, instead of subtracting, I'm going to add them. And this is amazing. So when I add them straight, the odd derivatives are going to be killed or removed, right? And then I'm going to end up with, on the left-hand side, summing the next point and the previous point. And I'm going to have, on the right-hand side, I'm going to have 2 times the current function, and then I'm going to have plus the second derivative times h squared, because 2 factorial, so it's going to be 1/2. So I'm getting a full second derivative times h squared. and then this kills, this kills. Remember, this kills, this kills, this kills, this kills. So now I've got the fourth derivative, cos C1, cos C2. So I just kind of let that hang around, and then I'm solving for, in this case, I'm going to be solving for f, the second derivative. The second derivative of my function evaluated at x sub I, and to get there, I divided through by h squared. So I've got h squared over here. And then over here, I had h to the fourth. Now I've got h squared because I divided through by h squared. And what that means is that my function, my second derivative of the function evaluated at x sub I is going to be an approximation of the second order, because that's the power that's left over in my error term, or what's come from my remainder term. Okay, so I could write it in this way, that the second derivative is coming from what's over here, divided by h squared plus that big O term. And again, remember that second order is kind of better than first order. If you think of h being 0.1, h squared is 0.01. So second order generally gives lower error than first order. So this conceivably would be a better representation. So this would be second derivative, because I've got an expression for second derivative. It would be second order because of what the power of h was in the error term. Okay, let's take a look at getting some higher order things. All right, so I'm gonna take what I had earlier, a forward step, a backward step, and I'm going to take those out to the cos C being the fifth derivative and the fifth power of h. Okay, so both of those. So backward step also to the fifth derivative of f and the fifth power of h. All right, so again, if it's a backward step, the odd derivatives get a minus sign. The even derivatives always have a plus. Okay, so forward step, everything's plus. Backward step, you have alternating minuses on the odd derivatives and odd powers of h. Okay, so remember that. All right, now if it's a double step forward, h becomes 2h. It's the same h that we had on the forward step, but we're just doubling it. So if it's a double step forward like this is, I need to think about a 2h. And since it's 2h and it's squared, so it's going to be 4h squared. If it's 2h for each h, that means that 2h cubed is going to be 8h cubed. 16h to the fourth, 32h to the fifth, because this is 2h to the fifth, so 2 to the fifth would be 32. All right, so that's a double step forward. A double step backward would be the same kind of thing, but again, alternate the minus signs on the odd derivatives or odd powers of 5. Okay, so the cos C's would be, cos C1 would be between the forward step would be between the current reference position and the next one. The cos C2 is, because it's a backward step, it would be between the previous point and the current point. If cos C3 is looking at a double step, so it would be between the current point and 2 ahead. Cos C4 would be between 2 behind and then the current point. All right, so do not proceed unless you feel comfortable with these equations and that you could generate them yourselves. It's very straightforward to do it. Very straightforward to generate these equations by yourself. Okay? So do not proceed unless you feel comfortable with these equations, how I've just presented them to you. We've got our current step. We've got our current step. We've gone 1 forward, 1 backward, 2 forward, and 2 backward. We've got cos C's for all of these carried out to the fifth derivative. Okay, so here's what I'm going to do. First thing is I'm going to try to go for a first derivative. I'm going to see if I can combine these things in such a way that I unveil a very intense first derivative. Okay, so that's what I'm going to try to do. So to do that, I need to think about how to combine them. So one way is I'm going to look at equation 1 minus equation 2, and then I'm going to look at equation 3 minus equation 4. And it's almost strategic that I do this, because if I do equation 1 minus equation 2, you can see that my first order in the first two equations, my first derivatives are going to combine, and the zeroth derivative and the second derivative and the fourth derivative are going to kill each other. All right, so I need to think about it from that perspective. When I do equation 1 minus equation 2, then I'm going to lose this term, this term, this term, this term. I want to, because I want to keep these. All right, so let's think about that. And then the second pairs, I'm taking 3 minus 4. So when I do 3 minus 4, I've got a similar thing where the zeroth order are going to kill each other. The second derivatives are going to kill each other because I'm subtracting this from this. 3 minus 4, so these kill. The fourth derivative kills as well. All right, so what I'm looking at is combining in such a way that I'm going to keep the first derivative and strategically kill other derivatives. All right, so the only thing kind of hanging around is the third derivative. So think about it this way, is if I do equation 1 minus equation 2, well, that's going to double up the third derivative, right? Because of this minus this, it's going to double it up because I have minus a minus. So it's going to double that up. And then if I were to do equation 3 minus equation 4, it's going to double those two up, right? Because it's going to be 8 minus a minus 8, so that's going to be 16. So up here I'm going to have this plus a negative, so that's going to be plus 2. Multiply that by 8, so that's going to be 16. And then I'm going to subtract off 16 because those get doubled up. And that's what happens. I'm going to walk you through that right now. So it's a little bit of strategy. So I restated those 4 equations. All right. So then I did 8 times the first one minus the second one. So I have that on the left side. What I have left here is f prime plus f prime, or 2f prime. All right, and then I have plus 2 of the third derivative over 3 factorial. And then I'm going to carry through with the Cassis. I'm going to let the Cassis kind of live a little bit. I'm going to give the Cassis a little air there, so leave them in there. All right, so that is what remains from subtracting the first one minus the second one and multiplying by 8. Then I'm going to take the bottom 2 and I'm going to subtract them. So I have I plus 2 minus my minus 2. And then here I'm going to have a plus 2 minus a minus 2. So it's going to be 4. Remember that the evens are going to kill. The evens are killing. What I have left is 8 minus a minus 8, or 16. And then I have 32, right? So I've got the 32 minus a minus 32. Maybe that should be 64 there. And anyway, let's forge on. Well, no, actually I'm okay, because I've got the 32 and the 32, and then I've got the 5 of the Cassis 3, and I have the 5 of the Cassis 4. So yeah, I'm okay. This is actually correct. Got myself thinking there for a second, but yes, it looks right. So I've got all my Cassis in. I've got my third derivatives in there. I've got my first derivatives in there. This 8 times this 2, though, is going to make it where I kill, because I'm going to subtract that top one. I'm going to take the top one and subtract out the second one. So it's going to kill the f triple prime terms, right? So we end up with 8 times 2 is 16, and I'm going to subtract off 4, so I end up with this 12 in front of the f prime. I'm going to have 8 in front of the I plus 1, minus 8 in front of the I minus 1. I'm going to have just a straight minus I plus 2 and a straight minus a minus I plus 2 and a straight minus a minus I minus 2. So I think I've said that right. And on the right-hand side, I've got the 12 f prime x sub I times h. And then I've carried through on all my Cassis. I think I have that all right. All right, so then, like I've been doing, I put my f prime over on the left-hand side and divide through by what would be 12h here. So I've got big numerator in terms of 4 points divided by 8, 12h. And then since this was an h5, I've divided through by 12h. So I've got the 12 hanging there, and I've got my h to the 4th. So this is going to be a fourth order approximation, or central difference of first centered difference, first derivative, fourth order. That's kind of clunky to say, but that's correct. All right, so you've seen finite difference theory. You've seen how it's based on Taylor's theorem. We did a forward, we did a backward, we did a centered, and we hopefully got a feel for what order means. And we did a very intense one right here, where we figured out a fourth order first derivative centered difference. Okay, so I hope you've